Hello. Today I will be making a video on quantum science and quantum computers, specifically the type of quantum science that can only be done within a quantum computer, because of specific properties that allow for quantum science to actually be realized within a quantum computation apparatus rather than a classical computer, which typically cannot create that kind of physical environment required to do the kind of quantum science that is no longer fiction and is actually real and um, could be right before our eyes. Okay, we will be covering several topics here. It involves teleportation, quantum teleportation. It goes over wormholes. It goes over quantum distributed processing. I have plenty of notes here. I have some articles to reference based on research. I also have some items to reference based on commercial usage of quantum computers and over regular networks, over the cloud, etc. So this is real, not fiction. It's up to you to make your considerations, but take a look at reality. Um, we've advanced very fast over the last decade and more, actually. You'll be surprised from this video just to see um, when quantum computation advancements really began and and um, and honestly, I think they're pretty cool, but also it might bring in other questions, such as why isn't it so open, right? Um, it should be. In my opinion, it should be very open and it should be common knowledge nowadays because this is something that will link a world that we aren't taught in culture, a world that we aren't used to at all. I have my reading glasses because there's plenty to read. So let's uh let's try our best to wrap our head around these ideas because this is real, not fiction. Okay? Alrighty. So um I will start this video with a Bible verse. You don't have to be a Christian, you don't have to be a person that loves Jesus. You could be anyone, okay? But I thought this has some pretty good relevance. So this is Ecclesiastes chapter 1, verse 9. It says, what has been will be again. What has been done will be done again. There is nothing new under the sun. Okay, there we go. That's our start. So classical computers work over electrical signals within a networked environment. Now, the classical computer uses a central processing unit, and also it uses graphical processing unit. There's tensor processing units, depending on whether we're talking about commercial data centers or your laptop, right? Much of these computers are actually very powerful. Even my laptop is very, very powerful. It's just that we haven't wrapped our head around how much power we have in the palm of our hand and how much power we have sitting on our desk or our laps. Um, for example, if you have a mobile device with a network band about 2.4 gigahertz or even 5 gigahertz, it's communicating at billions of hertz per second. And when you try to visualize that, when you try to imagine that, it is incredible. But our processors, our central processing units alone on our computers, our classical computers, um, can process information at speeds that um, if we tried to process information at the same speed as just our classical laptop CPUs, we might just fry our brains. it might be overwhelming. So our classical computers can already do a lot. We use them for genome sequencing. We use them for very complex computational models. We use them like nowadays we use them for artificial intelligence, right? Um, Rather than just tensor processing units or other advanced graphical processing units, just our central processing units alone have given us so much advancements in the world of technology, in the world. It literally brought the world of science uh, to life for us, and it advanced the world of science very quickly in a short amount of time. That's what classical computers have already done for us. Now, when I go through some of what quantum computation is revealing, because it is capable of bringing quantum science to life, and we can actualize that, we can see that, we can feel that, we can hear that. You'll see that it really bridges gaps of knowledge and gaps of technological advancements like exponentially. Like it collapses the gaps and it expands our technological advancements exponentially. Okay, so where shall we start? Should we start with something um, that's pretty much science fiction? Okay. But it's real now. Let's start with quantum teleportation. Okay. But first, let's go through a little bit about what quantum computers are, right? Um, Classical computers use bits. This is zero and a one, and these are processed sequentially, so one at a time, not at the same time. Okay. They're just done very quickly. So when you give a computer a task and it does it very quickly, you might think, wow, this computer just did all of that at once, or instantly. No, it just did it very fast. It just did it very, very quickly. It did not do it all at once, unless if it's a single task. And it did not do it instantly. It just did it very quickly. Okay. But quantum computers don't have to deal with zero or ones. Quantum computers use qubits, which can be in a state of superposition. So meaning they can occupy both values of zero and one at the same time. It can occupy multiple values at once. So this is the type of this is what allows it to be able to process multiple tasks at at a single process. So that would be instant, and that would be a single process where a classical computer would have to go through multiple processes very quickly. Okay. Also, they can also be linked through quantum entanglement, and we'll go over quantum entanglement some more. But it's a phenomenon that allows them to process multiple possibilities simultaneously and can solve certain problems exponentially faster than classical computers. Quantum entanglement also allows for two entangled particles, photons, or in other words, uh, uh, entangled qubits, right? So these could be physically distant nodes of information. Though they are distant, they are still linked, okay, according to quantum mechanics. And though they are distant, because of quantum entanglement, they are able to share information back and forth without traveling one or the other. It's almost like wireless communication. It's pretty cool. Okay, so let's go over what the University of Stuttgart was able to accomplish in 2025. But you'll see that as we go back in time, some of what they're doing today has already been achieved in a much more impressive style many years before, like a decade before. And when it writes that we're not really there yet, you will see that a decade before, we've already accomplished um, um, creating production-ready, commercially available quantum computers at very impressive qubits. I will show you all of these things. So it would allow you to start questioning, oh, sure, public university likes to get credit for things because they gain funding, but a private university isn't like a corporation or another private institution that really cares about competition and does not announce what they're doing because of competition. And they likely won't announce what they're doing because you and I are not their customers. Okay? But let's go through this. So the University of Stuttgart was able to accomplish quantum teleportation over a 10-meter separated environment using quantum dots. So these are separate endpoints where at one endpoint, the information is destroyed, and at the other endpoint, the information is regenerated. It's pretty freaking cool. Basically, the kind of teleportation we're sort of used to understanding, but there's other versions of quantum teleportation that were achieved, and you'll be very impressed as we go through this. So I'm going to read out loud some key points that I've highlighted from this research. Okay, so here at the University of Stuttgart, for the first time worldwide, this is a public university, right? We have succeeded in transferring quantum information among photons originating from two different quantum dots, says Professor Peter Mischler, head of IHFG and deputy spokesperson for the QuantumRepeater.net QRN research project. Okay, what is the background? Whether WhatsApp or video stream, every digital message consists of zeros and ones. Similarly, this also applies to quantum communication, in which individual light particles serve as carriers of information. So when we talk about qubits, when we talk about photons being sent or transmitted, traversable, or are entangled through quantum entanglement, so they're able to relay information back and forth to each other without traversing, without actually moving distances. We're talking about information being carried. You could also think about it like data, right? Data is being sent, data is being teleported in another way, because data is another word for information or digital information. In this case, it's on a classical computer, digital information or data does have its physical aspect. It's an actual physical electrical signal, right? But with quantum computation, we're using light, okay? And this is where fiber optics come into play, and you will read a little bit more about that. Cool. So another point here. An affordable quantum internet would use optical fibers, just like today's internet. However, light has only a limited range. Conventional light signals, therefore, need to be renewed approximately every 50 kilometers using an optical amplifier. Essentially, much of the world's internet infrastructure today, or at least most places are getting there, but a good chunk are already implementing fiber optics. Because quantum information cannot simply be amplified or copied and forwarded, this does not work in the quantum internet. However, quantum physics allows information to be transferred from one photon to another as long as the information stays unknown. This process is referred to as quantum teleportation. So they're achieving something different, but we will also see quantum information be sent through regular internet. Okay, quantum information before it is absorbed in the optical fiber They are to serve as nodes for the quantum internet. However, there are considerable technical hurdles. To transmit quantum information via teleportation, the photons must be indistinguishable. They must have approximately the same temporal profile and color. This is to ensure that what's being generated on the other end, because this here uses two quantum dots, one destroys and one uh, essentially regenerates, hopefully the exact same information on the other end. And here they're just kind of pointing out what has to be done. In these semiconductor islands, certain fixed energy levels are present, just like in an atom, says Strobel. This allows individual photons with defined particles to be generated at the push of a button. In the Stuttgart experiment, the quantum dots were separated only by an optical fiber of about 10-meter length, but we are working on achieving considerable greater distances, says Strobel. In earlier work, the team had shown that the entanglement of the quantum dot photons remains intact even after a 36-kilometer transmission through the city center of Stuttgart. So this particular experiment, remember, this is a public university, right? And there's other universities that have achieved something similar in a different way. They're all independently coming to pretty good results, right? We haven't even spoken about what the private industry has been doing for years or has accomplished. Again, it's competition, they probably won't. But for this particular project, they have a 70% success rate in teleportation. Okay, that's just about the information for this particular project. Okay, so now let's see what the University of Oxford has achieved. Okay, they're taking a completely different approach. Their approach is something that a a corporation might do, a technology corporation might do within a data center, right? In a data center, you have a whole bunch of uh, computer systems, but none of these computer systems act alone. They actually work within a distributed network of computers that can act as a single computer. But in this case, they distribute the work among many computers, okay, helping them achieve what a single computer environment, such as let's say an entire server rack, cannot do on its own, okay? So by creating a distributed network of computers, they're able to achieve a whole lot more than from a single one. So the University of Oxford is literally taking what's already there, right? An approach that's already there, an approach that's already working, and they're showing the approach of a distributed network of linked quantum computers or quantum processors can achieve much more than a single quantum processor. This is pretty cool. So let's go over some more of the highlighted parts of their research, and I'll also point to how a pretty good job they did because they're actually using methods that are already working for the industry on a larger scale. In a milestone that brings quantum computing tangibly closer to large-scale practical use, scientists at Oxford University's Department of Physics have demonstrated the first instance of distributed quantum computing using a photonic network interface. They successfully linked two separate quantum processors to form a single, fully connected quantum computer, paving the way to tackling computational challenges previously out of reach. Okay? In this new approach, small quantum devices are linked together, enabling computations to be distributed across the network. In theory, there is no limit to the number of processors that could be in the network. By interconnecting the modules using photonic links, our system gains valuable flexibility, allowing modules to be upgraded or swapped out without disrupting the entire architecture. So this is where they're taking what's already working in the industry, like a data center, right? Whether it's a regular data center or an AI data center, right? An AI data center essentially uses the same models as a regular data center that we've had for years. And essentially, they're linking a whole bunch of computers together to do a lot better computations than what a single one could. All right, let's keep going here. Next highlight point. These are linked together using optical fibers and use light, or another word for light is photons, rather than electrical signals to transmit data between them. These photonic links enable qubits in separate modules to be entangled, allowing quantum logic to be performed across modules using quantum teleportation. Okay. The concept is similar to how traditional supercomputers work. These are made up of smaller computers linked together to achieve capabilities that are greater than those of each separate unit. This strategy circumvents many of the engineering obstacles associated with packing ever larger numbers of qubits into a single device, while preserving the delicate quantum properties needed for accurate and robust computations. All right. So here it goes over some key terms, quantum entanglement and quantum teleportation. And you'll see how they relate to each other. And as I go over other information, these two are really important to remember because quantum computers and them working over the network really does rely on quantum entanglement. It makes them a whole lot more secure than classical computers because information doesn't have to necessarily be transmitted. The quantum entanglement, the quantum entangled particles essentially work as nodes. These are points that they can communicate with each other that can be vastly distant, physically distant. They could be in separate geographies. Okay, so quantum entanglement, where two particles, such as a pair of photons, remain correlated even where separated by vast distances. This allows them to share information without having to travel physically. Okay, quantum teleportation, the transfer of quantum information over long distances almost instantly using entanglement. How awesome is that? And when we say quantum information, it's like saying data, right? And like digital information. But we're talking about quantum science. So it brings into play something like entanglement, which is pretty cool. Okay, so in the next reading, these scientists were able to achieve um, quantum teleportation over a busy internet cable. So regular internet traffic, like a lot of internet traffic data was being sent through the exact same cable where they were teleporting quantum information from one end to the other end. Okay, and we'll read a little bit about how they achieved this. It's pretty cool. Northwestern engineers have successfully demonstrated quantum teleportation over a fiber optic cable already carrying internet traffic, introducing the new possibility of combining quantum communication with existing internet cables. They just proved it's possible. This was in 2024. The previous researches that we read were in 2025. They just proved it is possible. So if a public university was able to discover this with little funding, imagine, you know, uh, a business that has a lot more funding and doesn't have to publish things like this in order to gain funding. Okay, cool. Let's keep reading because this is really, really exciting. The discovery published in the journal Optica introduces the new possibility of combining quantum communication with existing internet cables, greatly simplifying the infrastructure required for advanced sensing technologies or quantum computing applications. Okay, here one of the scientists slash engineers, Prem Kumar, who led the study, is quoted saying, "Our work shows a path towards next generation quantum and classical networks sharing a unified fiber optic infrastructure." That is exciting news. Only limited by the speed of light, quantum teleportation enables a new, ultra-fast, secure way to share information between distant network users, wherein direct transmission is not necessary. The process works by harnessing quantum entanglement, a technique in which two particles are linked, regardless of the distance between them. Instead of particles physically traveling to deliver information, entangled particles exchange information over great distances without physically carrying it. Okay. The photon itself does not have to be sent over long distances, but its state still ends up encoded onto the distant photon. Teleportation allows the exchange of information over great distances without requiring the information itself to travel that distance. Wow, mind-blowing, right? We're used to sending things over the air or over the wire. But I mean, hey, if you really think about it, over the air is almost teleportation, but not in this way. This way is cooler. Okay. The next highlighted point. To test the new method, Kumar and his team set up a 30-kilometer long fiber optic cable with a photon at either end. Then, they simultaneously sent quantum information and high-speed internet traffic through it. Finally, they measured the quality of the quantum information at the receiving end while executing the teleportation protocol by making quantum measurements at the midpoint. The researchers found the quantum information was successfully transmitted, even with busy internet traffic whizzing by. Although many groups have investigated the coexistence of quantum and classical communications in fiber, this work is the first to show quantum teleportation in this new scenario. You'll see so many of these researchers are all saying this is the first time, this is the first time, but it's like, oh, another project is doing something like that. But this is cool because they're publicly showing um this is possible, right? At least maybe publicly this is the first time. Um I won't give them a fuss for that. They deserve the funding. We need more open information like this so we really know how advanced things really are. This ability to send information without direct transmission opens the door for even more advanced quantum applications being performed without dedicated fiber. Okay, the next point. Quantum teleportation has the ability to provide quantum connectivity securely between geographically distant nodes. Kumar said, but many people have long assumed that nobody would build specialized infrastructure to send particles of light. If we choose the wavelengths properly, we won't have to build new infrastructure. Classical communications and quantum communication can coexist. And this research here proves it. Okay, so I covered research in 2025 and 2024 on purpose. Because when we see this news, we like to think, oh my gosh, we're just making it. You know, we just started making it with AI, even though OpenAI has existed for over a decade, by the way, um, and had achieved incredible stuff. Um, but and with quantum science, through quantum computations, we could also think, oh my goodness, this is super new. But really, no, we can go back a decade and see that this kind of research was being done and very successful. One of these examples, we go back to 2012 at the University of Waterloo. Um, this is cool for me because I live in Canada and this is where the university is. Uh, but hey, what they did was very, very cool. Very, very cool. It definitely brings about very secure quantum communication. Okay, so let's just read what this is. Three IQC scientists were part of an international research team that achieved a record-breaking quantum teleportation across the Canary Islands. All right, that's a very long distance. If you don't use metrics, let's see what it is in miles because I use the metric system. So 143 kilometers is 88 miles, 88.8 miles. Okay, so for any viewers that use the imperial system. Okay, so back to 2012. An international research team, including several IQC scientists, have achieved quantum teleportation over a record-breaking 143 kilometers through free space. Wireless teleportation. The experiment saw the successful teleportation of quantum information between the Canary Islands of La Palma and Tenerife. The breakthrough is a crucial step toward quantum communications via satellite. The teleportation across 143 kilometers is a crucial milestone in this research, since that is roughly the minimum distance between the ground and orbiting satellites. The experiment paves the way toward teleportation of signals over free space, or even using satellites, said Jenna Wang, whose research is largely focused on the creation of large-scale quantum communications networks. Okay. Because there is less atmospheric disturbance when communicating upwards to space than between the Canary Islands, Makarov says the next logical step is to attempt teleportation between the Earth and a satellite. This was back in 2012. I added a note in red about a particular sentence that was said, and we'll go over that sentence with other material later. A particular sentence here says, and this shows that these scientists are pretty isolated. They're working on their project, they're so focused on it. They might not really focus on other developments outside of their own work, right? Because it keeps them way too busy, probably. So one of the person who is quoted here says, this is useful for applications in secure communications, as well as the possibility of networking full-scale quantum computers. There's no problem with that. It's what they say after that. Once they exist. Huh? Okay, this was in 2012, but we know that the first production commercially available quantum computer was sold in 2011, the year before that. So this was a 128 qubit a quantum computer developed by D-Wave, and we'll go over that very shortly. Okay. Um, so yeah, there. All right. So now let's go over the next part. Um, okay. So Google and partner researchers. Here at Google, using the Google Sycamore quantum AI computer. This is a part of Google's quantum AI Sycamore computer. And these researchers were able to achieve some really incredible stuff. This is a different kind of teleportation, not like what we demonstrated before, which was um, wireless teleportation in 2012, sending quantum information from one island to the other. The other was quantum teleportation over internet traffic, and the other was quantum teleportation over a distributed network of quantum processors, and the other was quantum teleportation over a length of two separated quantum dots, which perform something that we usually recognize as destruction and regeneration. Okay, so this is a different kind of quantum teleportation, but this quantum teleportation uses wormholes. So this is why you have to use a quantum computer to achieve these kinds of things. Only in a quantum computer can you create a physical quantum environment that allows for these abstract structures to be created, okay, to be actually created within the quantum apparatus, the quantum device apparatus. And once it's created in there, it is actually created in there. You use it to send information from one end and literally observe it, observe that information literally come out the other end. This is incredible achievement. Um, incredible achievement. And the amount of qubits they use to achieve this is like, oh my goodness, you only require that many qubits? Okay, so let's read some of the highlighted points. This is next level. All right. For the first time, researchers at MIT, Caltech, Harvard University, and elsewhere sent quantum information across a quantum system in what could be understood as traversing a wormhole. Though this experiment didn't create a disruption of physical space-time in the way we might understand the term wormhole from science fiction. So everything was contained within this quantum device apparatus. Okay? It's important. Calculations from the experiment show that qubits traveled from one system of entangled particles to another in a model of gravity. This experiment performed on the Sycamore quantum processor device at Google opens the door to future experiments with quantum computers to probe ideas from string theory and gravitational physics. A wormhole is a bridge between two remote space-time regions. In the classical general theory of relativity, nothing is allowed to pass through the wormhole. In 2019, Harvard University's Daniel Jeffress and his collaborators suggested a wormhole could be traversable when created by entangled black holes. These physicists discovered a quantum mechanism to make a wormhole traversable by introducing a direct interaction between the distant space-time regions using a simple quantum dynamic system of fermions, says Coltmeyer. In our work, we also used these entangled quantum systems to produce this kind of wormhole teleportation using quantum computing, and were able to confirm the results with classical computers. Okay, this is spooky action at a distance. In this experiment, researchers sent a signal through the wormhole by teleporting a quantum state from one quantum system to another on the Sycamore 53-qubit quantum processor. To do so, the research team needed to determine entangled quantum systems that behaved with the properties predicted by quantum gravity, but that were also small enough to run on today's quantum computers. A central challenge for this was to find a simple enough many-body quantum system that preserves gravitational properties. That's important. It has to preserve gravitational properties. It can't just simulate it. No way, says Zlokapa, a second-year graduate student in physics at MIT, who began this research as an undergraduate. To achieve this, moving on, the team used techniques from machine learning, taking highly interacting quantum systems and gradually reducing their connectivity. The output of this learning process produced many examples of systems with behavior consistent with quantum gravity, but each instance only required around 10 qubits, a perfect size for the Sycamore processor. That's incredible. They only needed to use 10 qubits to achieve this on a 53 qubit uh, Sycamore quantum processor. That's incredible. Once Zlokapa and the researchers identified these 10 qubit systems, the team inserted a qubit into one system, applied an energy shockwave across the processor, and then observed this same information on the other quantum system on the processor. The team measured how much quantum information passed from one quantum system to the other depending on the type of shockwave applied, negative or positive. We showed that if the wormhole is propped open for long enough time by the negative energy, shockwaves, a crucial path is established between the two quantum systems. The qubit inserted into one system is indeed the same that appears on the other systems, says Spiropula. Wow. Wow, wow, wow. Okay. So let's keep reading here. There's a note in red that I made, and this demonstrates the difference between a simulation and classical computers and what they actually achieved using a quantum computer with just 10 qubits. Okay? This is different from running a simulation on a classical computer, Spiropula says. Although one could simulate the system on a classical computer, and this was done as reported in this paper, no physical system is created in a conventional simulation, which is the manipulation of classical bits, zeros, and ones. Big note, here we saw the information travel through the wormhole. Major difference. Because on a classical computer of zeros and ones, if this were a simulation, it would just simply be a model, like a 3D rendered model. A classical computer cannot create the physical system, which is the physical quantum system that is capable of literally holding the quantum gravitational properties. That could only be done within a quantum computer using the 10 qubits, using the 10 qubit system that allowed them to demonstrate this successfully. This is what literally created the physical properties, the physical system of the wormhole within this contained quantum device apparatus. And as it's note, here they literally saw the information travel through the wormhole from one end to the other, and they were able to confirm that it arrived, the exact same thing that they sent through, the exact same information they sent through, literally arrived on the other processor. This is freaking amazing. Okay? This is amazing. This is really, really cool. All right. I had to explain that because you have to understand what they actually achieved and what can actually be done within this contained quantum device apparatus. It's freaking amazing. All right. And you won't see any visuals with this episode because every episode I make it with a lot of linguistic visualization. Because these episodes, all the episodes I make are meant for listening. So if you're watching, that's okay. Um, every episode is meant for listening. So you could just use it at any moment with whatever you're doing. Okay, so let's move on. Here we'll be able to see uh, Google Quantum AI Sycamore computer and a computer that sorry, a quantum computer that was developed by D-Wave, and one of its model, the D-Wave 1, one of its model was sold in 2011. Okay, so we'll start with um, Google Quantum AI. Uh, okay, all right, let's go over this now. It's actually pretty important. And we'll start with Google, okay? So here, this is information that I was able to find through Google searches. And much of this, honestly, you can also just search on Google. Don't worry about how advanced some of this technology is. Just take a look and know. It's good to just know where we're at. So the Sycamore quantum computer is famous for achieving quantum supremacy in 2019 by performing a complex calculation in minutes that would take the best supercomputers thousands of years. With around 53 qubits, it uses transmon qubits and represents a major milestone in demonstrating quantum advantage for specific tasks, though research continues to refine its capabilities and explore new noise-resistant operations. Okay, it was developed by Google Quantum AI, and the original version had 53 working qubits. It reached quantum supremacy in 2019. He performed a random circuit sampling task, so it performed a pretty advanced algorithm in 200 seconds that Google estimated would take a classical supercomputer 10,000 years. This marked a key demonstration of quantum advantage. That's incredible. That's incredible. In 200 seconds, it was able to perform a pretty advanced calculation. A supercomputer would have took 10,000 years. That's incredible. Okay, so by now, I'm sure the Google Quantum AI Sycamore computer probably has a whole lot more qubits. Okay, but let's check out another company that's not well known. This is not a publicly traded company, and they do keep much of their research private. Okay, and You will see here, while Google is announcing quantum supremacy with only 53 working qubits, in 2011, a company called D-Wave was the first to sell quantum computers commercially. So these were production-ready commercial quantum computers. Okay, these were ready for the private industry. These were ready for businesses. Um, you'd have to be very, very wealthy to buy it for personal use. Okay, but we'll see here. In 2011, one of D-Wave's quantum computer models called the D-Wave 1 was sold to the defense contractor Lockheed Martin. Okay, most people know Lockheed Martin. It's one of the most well-known defense contractors. They sell anything from like uh, data services, um, uh, very advanced technology such as fighter jets, very advanced technologies in communication, um, et cetera, et cetera. Most of these are used within the defense industry. Um, I guess their number one customer is the United States, and they have a list of clientele, like a list of clients, and that list of clients is not you or I. Okay, it's a private company. So they bought the D-Wave 1 quantum computer, and in 2011, the D-Wave 1 quantum computer model had 128 qubits. That's incredible. In 2011, production ready commercial quantum computer, 128 qubits. And at that time, Lockheed Martin brought it into their arsenal of advanced technologies. I don't know what they used it for. I don't. I'm pretty sure it's for one of their many advanced um, uh, technological projects and contracts that they have with various defense organizations and governments. Okay, so this is just one of their models in 2011. And these models, I'm sure you could link them, you could interlink them, just like how we read in the Oxford University's research, right? They achieved much more by creating a distributed network of quantum computers, in this case, quantum processors. So how much more can D-Wave or a company like Lockheed Martin achieve if they link all of their quantum computers within a distributed network? Just like what's already working for the industry, like a data center or an AI data center. All right, it's pretty cool. There's a lot going on. There's a lot that's already happened over a long period of time, and we might just be hearing about this. Uh, it's pretty cool. I remember reading something like this as a kid when I was looking into quantum computers and some about quantum science, and I was amazed, but I didn't really understand much and what the significance was. So if you're around that stage, take your time to wrap your head around this. So right now, concerning quantum supremacy, D-Wave demonstrate now is able to demonstrate some kind of quantum supremacy on material simulation. When we're talking about material simulation, we're talking about being able to create um, like uh, uh, physical properties within a quantum device apparatus. Okay, not like just software numbers being transferred back and forth. No, what we're talking about um, maintaining literal physical properties within a quantum device apparatus, like what the researchers were able to achieve with Google Google's Sycamore quantum computer. Okay, so let's see here. D-Wave did continue to make other models. Okay, they did not stop with that model. They created the Advantage model, which can solve problems in minutes that would take classical computers, again, thousands of years to accomplish. It's incredible. It's incredible what they're able to do. The Advantage model was created with over 5,000 qubits. Imagine a distributed network of um, linked of uh, of these computers linked together. Okay, each having about 5,000 qubits, and figuring out how to make them all work together. It's incredible. So now they have the D-Wave has created a newer model called the Advantage 2. And not only do they sell the on-premise devices that you can purchase and use for your business, or if it's a government, I'm pretty sure they can use it for whatever they want to use it for. Um, I don't know what they'll use it for, but we see that they can do some pretty cool stuff. Um, now they also offer cloud service. Okay, you can access their quantum computer over the cloud. Okay, and we'll see other companies are now offering this service. They've been offering quantum computer as a service over the cloud for quite some years now. Some started way back in 2016, some in 2019, and some are even selling portable quantum computers with around 2 qubits, 3 qubits, 5 qubits, etc. Right? These are portable, but if we're talking about the kinds that would make a data center, these are like 5,000 qubits or more. Okay. And we haven't even looked into their distributed network of quantum computers that is available and accessible through the cloud. Okay. So that's the two comparisons, okay? Um, it's good. It's good that we understand what's out there, right? And the types of advancements that are available. And if you're a person that really loves this kind of knowledge, and maybe you're already studying these things and you did not know um, um, how far we've went, maybe you might want to do a bit more and maybe get into the practical aspects of what the commercial industries are already doing rather than spending a lot of time with various small projects, and maybe you might not gain practical experience for the work industry. I know that's usually an issue for anyone studying things like computer science or physics, etc. It ends up being something that you might not be able to take full advantage of once you've graduated. And these companies nowadays are looking for like a broad range of experiences, right? Like just from the start. Many companies are taking advantage of AI in order to reduce the workforce. Amazon has recently um, literally laid off an entire workforce. Many people of that were software engineers. Facebook has been doing the same. Other companies have been doing the same. I know from the uh, uh, tech companies that I worked for previously, they've done the same thing. Previous companies literally removed entire job descriptions. Like that job doesn't exist anymore. That's because of technological advancements and the advantage that it gives these businesses. to be able to pursue their business goals while still being able to produce the kind of technology that they need with a much smaller human workforce. There's a lot to unfold with the advancements of things. Okay, and maybe we might cover a little bit more about that and what it might entail to people and the types of jobs that they do. Okay, so timeline of real world quantum computer availability. We've already went through production-ready, commercially available quantum computers in 2011, 128 qubits. Now we have way more, and I'm pretty sure the ones that are available within a cloud service are designed in a distributed network, right? Because these companies are not idiots. They're not new to this, right? Public universities might be new to it because like some of these research are working with less than $1 million, right? And the private industry, these businesses are working with hundreds of millions of dollars. Some of them are working with billions of dollars. Okay. So they can achieve way more much quicker and they don't have to announce it to anyone. So they have the competitive advantage. All right. Okay. So let's just check out some of these timelines because it's cool to go over some history and it allows us to understand the development of things. So there's a question here. What was the first quantum computer and when was it invented? So the first quantum computer in the world was a 2-qubit nuclear magnetic resonance quantum computer. It was an experimental quantum computer and it was invented in 1998. In 1998, the first experimental demonstration of quantum algorithm was reported. Researchers at Oxford University, IBM Al-Madden Research Center, UC Berkeley, Stanford University, the University of California, and MIT demonstrated the first experimental implementation of a quantum algorithm using NMR technology. So in 1998, the first quantum algorithm was successfully demonstrated using a 2-qubit NMR quantum computer. Jonathan A. Jones and Michel Mosca at Oxford University were the first to solve Deutsch's problem using this system. Shortly after, Isaac L. Chung at IBM Al-Madden Research Center, along with Mark Kubinek at UC Berkeley and collaborators from Stanford University and MIT, replicated and extended the experiment. Their work marked a significant milestone in quantum computing history. So here we see that what they all collectively learned, okay, in 1998 by creating a 2-qubit quantum computer and successfully running Deutsch's problem, which it was able to successfully solve in a single process, okay, where a classical computer would need to go through 2 processes in order to solve that problem. It demonstrated that quantum computers have an advantage over classical computers. This was already in 1998 a successful 2-bit quantum computer. Now they took that research that they worked on together and then took it to their respective organizations, okay, and continued extending that research. They extended that research much further from their respective places. And I'm pretty sure some of them were procured for other projects, either commercially or otherwise. Okay, so this is pretty incredible to see that in 1998 we were already working with quantum computers, and it was capable of solving the problem and demonstrating that it was something that had a much larger advantage than classical computer. And now we have companies like Google, Quantum AI, SpinQ, which sells portable quantum computers, Microsoft, IonQ, so many others. There's IBM. IBM now offers quantum as a service platform. So they're offering their arsenal of quantum computers over the cloud. Okay. So this allows you and I to create an account, and what we can imagine, we could develop quantum applications. Uh, I have no plan in developing a quantum application, but it's incredible to see that quantum computers, modern quantum computers, production ready, commercially available quantum computers are accessible over the cloud, um, so that we can actually expand technological advancements. I can only imagine, now I can only imagine um, giving some AI data centers access to something like a 5,000 qubit quantum computer or a distributed network of quantum computers that they could interface information back and forth. Because much of these data centers use fiber optics or optical fibers, right? Within their distributed networks. So it's something that is already compatible. It's something that could be relayed back and forth. They could essentially they could set up a node within each data center, regular data center, and AI data center, whichever. They could set a node, um, and using quantum entanglement, right, information is able to be relayed between the quantum computers distributed network. We'll call it a quantum computer data center, right, just to simplify it. It's able to relay and interface information within an exchange, right? In a matter of exchanging information back and forth, something that the quantum computers can take and mix together and bring forth what they need to bring forth. And classical computers and what they do, classical computers could also be implemented, or at least the infrastructure could be designed in a way that works with a distributed network of quantum computers. There's a lot of applications here. There's a lot of applications. And there's a lot that's going to be done. There's a lot that's already being done, to be very honest. Again, these companies have competitive advantage if they just don't mention much of it to the public. Cool. All right. Let's go over some differences between public institutions and private slash corporate institutions. So we have to ask ourselves, how come some of these public institutions are now demonstrating something like a distributed network of quantum processors? Um, the industry as a whole, the commercial industry the commercial industry has been working with that kind of distributed network model of computers for a long time. How come we're just trying to take that idea and use it with quantum computers, right? Um, and how come in 2012, researchers at University of Waterloo were able to achieve wireless quantum teleportation when we're just working with quantum teleportation with quantum dots in 2025, right? And how come in 2011, right, we were already working with production-ready, commercially available 128 qubit quantum computers. They were production-ready and commercially available to be distributed to customers, right? But now we still have that idea that quantum computers haven't arrived yet, but they've existed. They are an existing infrastructure. There's data centers of quantum computers. This is like some people that might still say, "Oh, AI hasn't arrived yet. AI hasn't arrived yet." But it's like we have entire data centers dedicated to AI, and it works incredibly. Microsoft, 30% of Microsoft software is developed using AI, right? Um, it's incredible. It's incredible. This is why a good chunk of companies are laying off software engineers because we have very intelligent machines, right? So the maintenance of the classical knowledge that we've had for so long is still something of some kind of importance. Maybe it's a type of ignorance, I don't know. But quantum computers are production ready, commercially available. There's data centers of them. Just like AI isn't anything new anymore, right? It's something that should be common knowledge by now, and I want to promote these things like it is common knowledge so that it's no longer jargon or gibberish. It should be something that's well integrated into our common understanding, our common knowledge paths, something that allows us to grasp the advancement of technology at some growth, right? Rather than still thinking that it's fiction. No, it's completely real. It's very real, right? And it's all up to you, the types of determinations that you make. Whether you're going to be very realistic and say, "Oh, okay, this is really a part of our life and has been for decades," or maybe just deny it, and hope that um it stays that way. Maybe it just might, but I'm one of those that says it should be common knowledge. It should be. It should be common knowledge. Alrighty. So I have a final note here, and then we'll go over some terminology that are pretty important in reference to some of the items that we have discussed here. This is a long video, but at least it's made for listening, so you can always pause, leave, come back, and you can always, pause and play another day. Okay, but we're almost done here. So, final note that I wrote here. Okay, because quantum computers can work over regular internet infrastructure without teleportation, modern quantum computers are more powerful and well integrated into our everyday infrastructure. With teleportation comes a whole entire new world of quantum computers working with our existing infrastructure. Okay, um, with the model of using nodes. These computers can easily outperform classical supercomputers, making calculations that would take a classical computer, a classical supercomputer, thousands of years into mere seconds or minutes. With the use of quantum computers, we have to consider where quantum science now comes into play. Because we understand that quantum science completely obliterates classical science, we should start to realign our minds to the possibilities that exist beyond what we know and have been used to for centuries. Quantum computation with AI is capable of bringing advancements which were unimaginable or at least limited to science fiction movies. But now we can see that what these technological advancements are doing is bridging the gap of impossibilities in just a few years or even months. The creation and usage of a computational wormhole, the way created using Google AI's Sycamore quantum computer is next to impossible and just outright ridiculous if it were done using even a classical supercomputer. Now we are even factoring teleportation of data in quantum states over existing network infrastructures. Quantum computers and quantum science is not just for public universities and their independent respective experiments. These technological advancements are now very common within the commercial space. Nowadays, people can purchase quantum science hardware and quantum computers for personal or business use. Many businesses such as IBM, Google, D-Wave, and others have even opened up their arsenal of quantum computers for anyone to use over the cloud with quantum computers as a service. This is like Amazon Web Services or even Microsoft Azure. Users of these quantum computer cloud platforms can utilize them in any way imaginable. Okay, so all right. These are extra definitions here, okay? Because quantum computers are what I call the quantum device apparatus required to hold the physical quantum properties, okay? And these physical quantum properties allow for really advanced science to be done within this quantum device apparatus. It will literally create the physical property, and it will literally allow for the quantum sciences to be actualized. Okay, one of these is quantum sensing. Okay, here quantum sensing uses principles of quantum mechanics like entanglement and superposition to measure physical quantities with unprecedented precision. These technologies can sense time, gravity, magnetic fields, and more, enabling applications in personalized medicine, geological exploration, navigation without GPS, and advanced materials research. Quantum sensors are sensitive to minute changes in their environment and offer the potential for performance beyond the limits of classical sensors. Okay, quantum superposition. A core principle where a quantum system exists in multiple states simultaneously. So different locations, different spins, different energies, until measured, at which point it collapses into a single definite state, acting like a wave that can be in many places at once. Okay. And when we say acting like a wave, it demonstrates that photon, light, okay, is essentially the same as a wave, okay? This goes into entire topics of light to frequency conversions and frequency to light conversions, okay? More advanced stuff, but it's good to actualize because not only is there more advancements in quantum science, but there's more advancements in wireless-based technology, right? Okay, quantum entanglement, a phenomenon where two or more particles become linked in such a way that they share the same fate or information, regardless of the distance separating them. All right, there you have it. Quantum science and quantum computers, or at least how to achieve quantum science. You must have a quantum device apparatus. Okay? You cannot use classical computers, even a supercomputer. Okay? And just for those that are still trying to develop their technical understanding, a supercomputer is like a data center. It's a distributed network of individual computers that work together in a form of a cluster. And this cluster essentially creates the notion of a single computer. That's why it's called a supercomputer. It's not one gigantic single computer, but it's many computers working within a cluster, and this creates that identity of a single computer. Okay, it's pretty cool. It's pretty cool. All right. Ah, my name is Ezekiel Amani, and I just brought you some pretty cool information. I will link some of the research in the description. Feel free to go over it yourself. Feel free to listen to this episode again if you would like. Um, and what you take from it is up to you. But there's a vast amount of development within this space, and it becomes more advanced almost every year, almost every month. And with the usage of AI in the way that that the leaders of the corporations want to use them, literally makes this research into something that um, is actualized very, very quickly. It's incredible. I'm still amazed that in 2011, production ready, commercially available 128 qubit quantum computers, and now we're just working with much more advanced quantum computers that are capable of pretty cool quantum science. Now, I will also note, uh, even though there are already a vast amount of uh, quantum computers within what would be like a data center, they're already available working over networked environments, and you can relay with these quantum computers in the way that the researchers who used the Google's Sycamore quantum computer. You could relay with these quantum computers using your classical computer, right? They will do the work that quantum computers are supposed to do, and um, you could relay and convey what you need to convey using your classical computer. That's pretty cool. Even though all these things are already available, there are partnerships between various companies to help them gain the type of competitive advantage that they did not have, or that they may lag behind if they don't work in partnership. Whereas other businesses already have this kind of competitive advantage because they have their own data centers, and these data centers essentially act like their own internet service provider. Okay, it's pretty cool, and it's pretty interesting how they can do that. Um, but companies like IBM don't necessarily have the larger scale that other companies have. And so they've partnered up with Cisco. Cisco is one of the world's largest telecommunications company. And they're working together to build a large scale network of fault tolerant quantum computers. They want to be able to actualize a quantum internet using their existing infrastructure, IBM's existing data centers of quantum computers, and IBM's existing telecommunications infrastructure. Essentially, they make the devices, they make the software, and now, hey, let's partner up and have some kind of competitive advantage. If you're paying attention to partnerships between many businesses nowadays, you will see that even NVIDIA, NVIDIA is the world's largest provider of graphical processing units, tensor processing units. These are units that are used for AI, for gaming, for very advanced video processing, very advanced calculations. So now NVIDIA is partnering up with OpenAI. NVIDIA is partnering up with Nokia in order to use their existing telecommunication infrastructure worldwide to bring AI at the edge. Essentially, that means that AI would be able to work on these individual network environments or nodes and be able to advance their technological goals much faster so that they can actualize it and realize it. So IBM is seeing that now they need a competitive advantage. They already have a quantum computer as a service environment, and Cisco already has a good chunk of network infrastructure. They make networked devices. And so this kind of partnership also helps them gain some kind of competitive advantage. It's all about competitive advantage, right? So we will be seeing a lot more from so many companies, and how they will use all of these advanced technologies together to give themselves competitive advantages within months, within 2 to 5 years, within etc. Right? And those that are already actualizing and realizing their competitive advantage, well, they made it, and they're probably not going to give anyone else the competitive advantage by making public announcements. Anyways, I hope you found this information useful. Um, I hope it was as simplified as possible. It's not simple. It's not simple to make these information uh, easy to understand, because we're still using terminology that's within quantum science, a pretty advanced section of science that hasn't been given to the common population, right? People like you and I as much for years. I'm just grateful that I grew up, being really interested in these types of science and technology, and so I just ended up reading a whole bunch of stuff. Um, but I really do hope that very soon they will really push for common knowledge, and they will push to really bring these terminologies into something that is less less like less um I hope they will simplify the terminologies, okay? That's what I'm trying to say, so that it's not something that only scientists would understand right away, or people that have read about the terminologies a lot, right? So that'll be all for now. Maybe there will be another video about similar topics in the future, but here I make videos for you to listen to or watch. It's up to you, right? And my videos are around science, technology, faith, and understanding the world around you as best as possible, the way that you can convey to yourself to understand. Okay, cool. Bye bye.